Hello and welcome to the series of lectures on reinforced concrete design. Now the first question that we should answer is why reinforced concrete. So if I take any beam, let's say simply supported as shown here, and subjected to a gravity loading, the corresponding deformed shape would be something like this. Now if we observe closely, this deformed shape has some fibers getting compressed whereas some fibers getting stretched. So this, if you have studied theory of pure bending, this is very consistent with what we have studied for theory of pure bending. So if I draw the bending stress distribution for the same, if you recall, the formula was sigma by y is equal to m by I, where y is the distance from neutral axis, because we have two separate exactly opposite to each other behaviors like compression and tension. So they are exactly opposite, and we want to find, if let's say maximum stress in compression, so we'll have to substitute the value for yc, and if I need maximum tension, I'll have to substitute value for yt, and that depends on geometry, that is moment of inertia as well as the magnitude of bending moment. So we are familiar with this. So we need a material which will be equally strong in compression as well as in tension. So the material that comes to our mind, wherein we can have another advantages like having a general form whichever we'll give through form work, so that is a reinforced concrete. Now reinforced concrete is made up of two distinctly different materials. First is the concrete. Now concrete is made up of cement, coarse aggregate, fine aggregates, and of course water. Now this concrete as a material, we need to get the compressive strength, because we are expecting that the concrete will resist compression. And similarly we have reinforcement. So at what strength this will yield, that is more important to us. So if I see compressive strength for concrete, and if I know what is the yield strength for steel, I am capable of resisting these bending stresses. So that is the key for making the reinforced concrete. So there is a fundamental assumption that concrete will resist compression and reinforcement will resist tension. Now, are there any requirement for material qualities? Of course there are. So we will have to refer section 2 of IS 456 to get the qualities of the material. Now what are the design philosophies that we follow? So generally we started with working stress method of design, then we went to ultimate load method of design, and finally now the current practice is to follow limit state method of design. So we'll be focusing on limit state method of design. Now what is a limit state method of design? There are two classifications of limit state method. One is the limit state of collapse and other one is limit state of serviceability. Now these are defined in IS 456 in clause 35.2 and clause 35.3. Now if you see that there are 4 collapse limit states. So if there is a member, now in what ways it can fail? It can fail in flexure, it can fail in shear, it can fail in compression, it can fail in torsion. So for all these 4 actions, my structure should be capable of being safe under any extreme event. Now serviceability comes under deflection and cracking. So our structure should not have excessive deflections, nor they should show excessive cracking. So subsequently when we'll go for design, we'll go ahead with all the limit states and see applicable clauses. Now we'll go ahead. Now there are very important recommendations given by the code regarding the strength. So if we want to see what is the characteristic strength of an material, for example, let's say concrete for that matter, or even steel for that matter, so we'll have to refer clause 36.1, and that will give us what is the characteristic strength of the material. Let's go to clause 36. Now that gives us characteristic strength as well as characteristic load. But for the time being, let's focus only on the characteristic strength. Now the characteristic strength means that value of the strength of material below which not more than 5% test results are expected to fall. So we'll have to test the material in laboratories. 95% strength should exceed what is our characteristic strength. Only 5% test results are expected to fall below the expected value of characteristic strength. In addition, there are some factor of safety is defined for material strength. They are given in clause 36.4.2. Now these factors, if we visit the clause again, there are two factor of safeties for two different materials. Like concrete we have 1.5 and steel we are having 1.15 defined in clause also. You can visit that. Now let's start the journey of limit state design, and let's start with the first limit state, that is limit state of collapse due to flexure, or in simple words, bending. Now this is given in clause 38. So let's go to the clause. So limit state of collapse, flexure. If you see, there are some assumptions, and basically we are having two different materials and we have different factor of safeties. So code tells us certain values for stresses and strains. So if we see, the maximum strain in concrete at outermost compression fiber should be taken as 0.0035 in bending. So if I go to this, so this is, let's say, a singly reinforced section wherein B is the width, capital D is the overall depth of the beam, small d is the effective depth that we'll subsequently see in much more detail. For the time being, let's understand that this is up depth from the top to the centroid of the reinforcement. Okay, so again it is very similar diagram to what we have seen for theory of pure bending, but here the stress diagram looks little different, and we'll see because this is from the assumptions of reinforced concrete design using limit state method. So first of all, let's go with the value that we got. So maximum strain at the outermost fiber in compression is 0.0035. So I can put a value here which is now 0.0035. This is told by the code. Now in addition, they tell us what is the strain in steel also. So if we go down, this tells the maximum strain in tension reinforcement in section at failure shall not be less than Fy by 1.15 times Es plus 0.002. So if we just use a calculator and let's divide that Fy, let's say the 1 by, let's say, 1.15, so we'll get a value of 0.87. so if I just press this, 0.869, so we can treat safely this as 0.87. so this factor I have calculated 1 by 1.15, so it would be 0.87 Fy divided by Es plus 0.002. so let's write this down. It would be the strain in steel at failure would be 0.87 Fy divided by Es, that is modulus of elasticity for steel, plus 0.002. Let's verify again. Yes, it is the strain in steel at failure, or outermost fiber, we can say, right? Now the code again says that the maximum stress, now we talked about strain, let's say the stress that we need. So for design purposes, the compressive strength of concrete shall be taken as 0.67 times of the characteristic strength, and further we'll have to apply partial safety factor of 1.5. so let's say we are having 0.67 as our strength okay, this has to be divided by 1.5 because this is the partial safety factor for concrete. So if I press is equal to, we get 0.446 as our outermost stress in concrete. So 0.446 FCK would be, FCK is now the characteristic strength. So we are, as per the codal recommendation, 0.67 times of the characteristic strength, and further divided by 1.5, which is the factor of safety, that comes out to be 0.446. Okay, so if I go back, so in stress diagram I can now write that my stress value, this is the maximum stress value, so this comes out to be 0.446 FCK. Further, if you see the stress diagram, they are telling us that the stress distribution profile can be rectangular, can be trapezoidal, can be a parabolic, or any other shape and there is one typical curve shown in figure number 21. So if I go to figure number 21, we can observe few things. So this is the parabolic curve, and this is our FCK value. Now the interesting observation from this, the distribution of stress is parabolic up to the strain of 0.002, and afterwards it becomes linear. So this is one point that we need to really plot on our diagram. So after 0.002 strain up to 0.0035 strain, we have linear variation, and up to 0.002 strain from the origin or from the neutral axis, the distribution is parabolic in nature. This is one acceptable stress strain variation given by the code. So here also we can see FCK is the characteristic strength. We are told to use 0.67 times of that. Of course, there are so many reasons. If you want to go in much more detail, there are reasons for that. And further, we are dividing this 0.67 FCK with the factor of safety, which is 1.5. That is how we get 0.446 FCK. So if I can go here and plot the same point, which is 0.002 strain. So if you see, our stress strain diagram is also linear up to here. So this is a linear portion, and this is parabolic variation. Okay, so this one is parabolic variation. Now up to what linear? So code clearly told us that if your value of strain here is 0.002, here is our neutral axis, so up to 0.002 strain, so this value we take the projection, and the variation in stress is parabolic in nature. Beyond 0.002 strain up to 0.0035 strain, it is linear. Okay, so this gives us recommended values of stresses and strains as per clause 38.1, which is the fundamental assumptions for limit state of collapse. Now subsequently we have to calculate so many design constants, and then we can go ahead and design singly reinforced beam, then doubly reinforced beam, because this is the heart of limit state method of design flexure assumptions, which we can subsequently replicate to slabs also, and even to footings later on. So this is a very key concept. Okay, so in next session we'll derive the design constants and subsequently take it ahead. Thank you.